Thanks, Rich. Um, I want to, often these Pangeo showcases are used to showcase something that somebody's already built, but the discussion part of today's meeting should be part of the point, because what I'm trying to do here is use the presentation slot to propose ideas for community discussion. So let me just share my screen and see that. Okay, so I'm going to talk for like 15, 20 minutes, hopefully, and then turn it over to a group discussion. I'm speaking here in a personal capacity. I'm actually between jobs for a couple of weeks. This is just something I've been thinking about for a little while. And I basically want to argue that there's a missing link in the way that we share scientific data that would be of interest to many different organizations. So what I'm not going to talk about today is the details of this blog post. I published this a couple of weeks ago. There was quite a lot of interest. I know some of you here today are here because you read this and thought it was interesting. This was the title of it. Instead of just rehashing this, what I want the direction this blog post went in was kind of like product design, like what features we would need in a network for sharing data, but without talking so much about the technical side of it. Instead, what I want to do in this talk is go in the opposite direction and start from what technology we have today and build up towards how close we are to realizing something like this. So what I will talk about is the state of version-controlled cloud-native data sharing today, then this problem of connecting the catalogs, the use cases that enables. In order to enable those use cases, I think there's this common missing link, which I'm going to call Frost, and then design ideas for how one might go about making such a thing. So the current situation today is that every organization that provides data tends to have a separate walled garden, whether it's a public agency like NASA or NOAA, or whether it's some kind of like research group or startup denoted here by a rocket ship. They tend to have these kind of like separated little entities on the internet that aren't like directly connected to one another. Inside each of their walled gardens, like for a long time, they would just have a complete zoo of different files, file formats. Every data set might be made up of multiple different file types, like maybe the apples are netcdf files, the orange are grid files, whatever. It's generally a mess. Cloud native data formats simplified this for us massively. And one important way that they did so is they basically allowed us to collapse the concept of a single data set being something that consists of thousands, millions, or sometimes even billions of individual files down to just a single URL that points to a ZAR store or a Parquet table or whatever in an S3 bucket. So that means that once we had ZAR and Parquet, this problem of data sharing mostly reduced to the idea that one data set equals one URL. But you can go even further than this. And we have done more recently with version-controlled formats such as Icechunk and Iceberg. Now one data set can be even more specifically specified using a single URL and a single version hash. And this is super powerful because now you can point to like literally, you can uniquely specify a petabyte of data with, in theory, with a single URL string and a single version string. And you know where it is, it's self-describing, so you can learn what's in it. It can be publicly accessible through the S3 storage, and you have an idea of what version it is, and you have the infrastructure to change that version and update it and publicly see the history of versions. So this is a super powerful primitive. Once you have this ability to specify any data set with just 2 strings, you could extend this to relationships between data sets, also specified as tuples of 2 strings. So if one data set is in some way derived from or related to another, if you can specify any data set with 2 strings, you can specify any dependent of a data set with another 2 strings. And here this is like a way of describing a single data set. But if you zoom out to every possible organization and every data set in every organization, this now means that describing every data set in the world is just a long list of URLs, versions, and then their dependent. tuples, dependence tuples. And so this long list is effectively then a registry of all the scientific data that anyone might care about. Obviously, this list does not exist in any one place right now, but it could. And it only could because we have these cloud native single URL, but very scalable version controlled formats. So if you imagine somehow creating a single registry across all organizations, it would be federated between organizations. It would be a registry of all different scientific things. So I'm provisionally just called it FROSS, the Federated Registry of Scientific Things. Some cool features get enabled by this. If there's an update to some data set that causes it to bump its version, if you have a network, you could propagate notifications of that update to other data sets in the network and then update those based on the notification it just learned about. This is especially used, this is a concept that's useful in like all fields of science because you potentially always want to know if the data set that you derived your results from was updated because maybe it was wrong. But it's especially useful in geoscience because we have new data arriving every day, like every hour potentially, in the form of satellite data, which is what this GIF is supposed to show. And we have a lot of data sets that are effectively derived from common upstream data sets. So some kind of like notification system is clearly quite useful within the geoscience case, and people end up building versions of this regularly already. So what's the problem that we're trying to solve here? The problem is that everybody makes a catalog, but all their catalogs are disconnected. This means that there's no single place you can go to discover every data set that you might be interested in. There's no easy way to propagate updates between organizations. There's arguably a risk of like a catalog wars developing because different platform providers have an incentive to have like more data sets available within their platform service. And then there could theoretically be a race of like who's got the most data in their catalog. And then if somebody managed to become dominant in that space and have a huge amount of everyone's data listed in their catalog, then if it's not federated, you potentially have a risk of like network lock-in, similar to like the difficulty of migrating off Twitter when all of your follower network is like stuck in Twitter. So the solution is to connect the catalogs. And it would allow, because if you have some way of connecting all the catalogs, you can allow cross-org discoverability, cross-org update propagations. There's no incentive to try and catalog everybody else's data if you can already search the entire thing. And it alleviates any risk of lock-in because if you have control or the ability to export the follower graph easily, you can always move service more easily. So if we imagine for a moment that this cross-org catalog registry thing exists, then it enables a bunch of different platforms and services and useful tools to all be built with a very similar looking architecture. And that architecture looks something like you have various user communities. Each user community is potentially served by different websites, different search services, different platforms. Maybe the NASA scientists are served by one thing or whatever. But all of those platforms are searching across a universal federated registry. The registry contains those URLs, which either get you straight through to some data, or they make you go through some kind of authentication portal before you can actually get to the data. And that might be, they might let you straight through to the S3 storage because the data is just fully public and openly licensed, or they might require authentication because it's private data for some reason, or maybe it's like sensitive biomedical data or something like that. There's like valid reasons to have an authentication layer in between the registry and the storage. But so long as they're separated, you can insert any kind of authentication layer you want there. The URL doesn't have to take you straight to a public bucket. So what kind of use cases would this kind of architecture enable? So an obvious motivating one is just a public data catalog, for example, like a catalog of NASA data. And in practice, that looks something like having a NASA-specific search tool, so a website that lists all NASA data sets, which itself is derived by querying a federated registry. and queries it for the URLs that point to NASA public datasets in public S3 storage. Another similar use case is to have a aggregated search engine. Like Google has this dataset search page for searching across all sorts of public datasets. But if the registry is open, then people without the resources of Google could also create search services on top. And these could be, if somebody thinks there's a gap, like maybe they think that every oceanographer would benefit from a tool that searches, that immediately displays every data set that has the word ocean in its metadata somewhere. They're free to build that if the registry is publicly accessible. A data marketplace is quite similar, except it has some kind of pay for access layer inserted between the list of what data is available and the actual place that you get the data. And so, for example, this is what Source Cooperative has publicly said that they intend to build. And this is like a little bit similar to Facebook Marketplace, this design, where people list the price, but then the actual price gets negotiated only once you like talk to the buyer. But it could be done with an architecture like this. In sort of biofields, they have this interesting problem where they're often not allowed to let the data move away from the place where it's stored because it could potentially get leaked, which would violate HIPAA. And so there are these what are called federated data analysis, and federated here means basically federated storage, or federated data providers rather than a federated like actual platform. But they work in essentially the same way as the marketplace. There's some platform that has some internal registry that has a authentication layer that proves that you are where you prove that you are actually like a medical researcher, and then that allows you to run compute at the location of some sensitive data. A data lake is also quite similar in that you have a platform service, a registry for data which might be private or it might be public facing. You only want your customers necessarily to be able to access the data, or like your engineering team to even know that it exists. So you have an authentication layer, and then the storage itself is behind some kind of data lake features that are what their customers are paying for to improve the speed of their queries or whatever. Another thing that you could build much more easily if this registry existed would be some kind of backup trawler or archiving service, like analogous to how the Wayback Machine archives websites across the whole web. In this case, it's easier to build the archive if there's already a registry with all data sets on it that regularly gets updated, because you can just trawl it and start sucking the data out. But you can also then put the backups back up on the registry for other people to see. The final important use case that would be made easier if you had some kind of pub sub like automatically updating registry would be alert services that require real-time operations. So the Watch Duty nonprofit that suddenly became very important during the LA fires recently is an interesting example. Like, I don't know exactly how they determine where fires are broken out, but in theory, some organization like them could wait for and ingest like thermal imagery from public satellite data, watching for updates via the registry, and then as soon as an update is available, they quickly recompute like new wildfire risks or send alerts to people's phones or something like that. So in all of these, clearly there's a common missing link, this decentralized publish subscribe catalog network. So what I want people to think about is like if we were to build this, like how would we do so? We just have to start with a list of technical requirements. So the requirements are that we define entries in the catalog, we define updates to the catalog, to the entries in the catalog, and then dependencies between entries in the catalog. We want the entries to be able to handle any data that's at some S3-like URL, and the data needs to have some kind of version control hash. We also want our hypothetical system to be able to propagate update notifications in a fast, sort of reliable, eventually consistent kind of way. And we also would like it to be federated, because something like this would be so large that it wouldn't be ideal to just have a single organization controlling the entire thing. And really, a single organization is not going to be able to be sort of all things to all men and serve all users. That's kind of the point of the architecture above. And nevertheless, even though you want it to be federated, you still want to enable global search, which is kind of what makes this a little bit tricky because those two things are often in opposition. You want to be able to enable global search across every field because if you don't, you're arbitrarily drawing lines along organizational or sort of scientific field boundaries in a way that's going to like break somebody's like professional network effectively. So with that list of requirements, like how could we possibly build this? So we could look for inspiration in some other systems. So one example would be publish subscribe protocols. There are open protocols like RSS for subscribing to blog feeds or like the email protocols. These are quite interesting in that these are like totally decentralized. Anyone can subscribe to anything basically, and updates propagate relatively quickly. Another interesting sort of similar thing that already exists are recent attempts to build federated social networks because the dependencies between data sets are kind of like following people's posting on different profiles. So the posts are kind of like data entries, like new versions of the post or replies to the post are kind of like updates. And then if you sort of follow or link to things, that's kind of like the dependency. So it's kind of similar. And Twitter is completely centralized, so fails the like federated requirement, but both Blue Sky and Mastodon are interesting experiments that have underlying open protocols for creating federated social networks. It's also a little, you can also think of this like as a database replication problem, like the global list of all entries of all updates and dependencies can be represented fairly straightforwardly as a database. And then the problem is just like, how do you make sure every organization has the same database? But there are algorithms in this kind of area for this kind of thing. It's also a little bit like a software package registry because you have this sort of graph of dependencies and you might potentially want to like be able to publish new things, change the dependencies, and then also sort of resolve and traverse the dependencies. So it's a little bit like NPM for JavaScript packages, whatever. So just to throw a couple of ideas out there before we take it to discussion. One idea is leaning on this database analogy. You could think of it as like cross-org database synchronization, and you need to do it in some like leaderless way. But first you have to describe the schema. The schema has to have an entry, a version, and dependency tables. So like the entry tables has like a URL, the name of the data set, when it was created. Then for each entry, there's versions which have certain hashes, but you can have multiple versions for one entry. And you want to know when the last one was updated. And then for each version, it potentially has multiple dependencies, which can be described in terms of like individual entries upstream and downstream, like dependents, dependees. This is just like a very rough sketch. But if there was some kind of cross-organizational standard or agreement on what the schema of this database was, and then a protocol through which it should be synced, that would be one way to build like this kind of cross like network thing. Another idea, which I don't really think is the way to do it, but it's quite an interesting rabbit hole that I went down, is Blue Sky, the social network platform, is federated through this thing called the AT protocol and it's used for Blue Sky, but it's actually very general and is used for this like little ecosystem of applications called the atmosphere, they call it. And you can use it to do all sorts of interesting things. Like you can go and just like consume the stream of all data of everything that's being posted on Blue Sky right now. But you can even use it to, if you do something called defining a custom lexicon, you can actually like define your own sort of type of social media post. So instead of like a text post, you could define like a dataset post. And I messed around a bit with this and was able to sort of define something that looks like an entry for a single data set and an update for a single data set and a dependency for a single data set. The way it works in Blue Sky is you publish these from something called a personal data server. the set of all the things that's being published goes into the fire hose, which can be consumed by anybody, and then can be filtered down and displayed via a feed gen. So in this case, like the feed gen is like displayed as like the NASA catalog or the oceanographer specific catalog or something like that. Whereas the platform services would basically help you run your PDS. And the platform services would pay the infrastructure costs for consuming the fire hose. But after looking at this for a while, I realized that if you consume the whole fire hose forever and you also want to know about everything that was ever published on the fire hose, at that point, you basically have just like done a long way around to just getting a whole database. And you may as well have just thought of it as syncing it in a database in the first place. But the reason I brought up the AT protocol is that because once you have a federated registry, it opens up all sorts of interesting things for like ideas for linking scientific publishing to social media. Like it's not impossible to imagine like Blue Sky, the social network platform, is able to bidirectionally link to every piece of scientific data that ever gets published. It's going to advance. Yeah. So here's a bunch of ideas for people to discuss, and hopefully we can have some fun discussion now. But before then, I just want to float this idea of like a little sort of working or discussion group to talk about these ideas going forward. And like, what would we do? Would we make a standard? Would we make a protocol? Does something like this already exist? There are definitely efforts in this general direction, but I contest that the recent advances in like cloud native storage have meant that we can do this in a simpler way than previously. This would have to be a multi-organization effort. Like if it's federated, there's no point in a single organization doing it. It would only make sense if multiple organizations were all like interested and committed to doing it together. If that sounds interesting to you, I just made a little Google form to indicate your interest there. So yeah, that's my presentation. Please, questions and then discussion. Thank you.
Hey, thanks a lot, Tom. That I know that's going to generate some discussion. And if you'd like to start the discussion, just go ahead and click on the little raise your hand, which is under the heart now, on React at the bottom. So first React and then raise your hand. Let's see. Do we have some hands? Ian.
Am I here? Yes, there I am. Okay. Well, I'll just get the ball rolling. Because I think there'll be a lot, because this is very fascinating, and I know it's something we all think about a lot, and I really appreciate the thoughtful blog post you wrote in this session, Tom. I keep coming back to the similarities between building data artifacts and building software artifacts. And you mentioned things like the NPM registry, but another part of that is the build system, and we don't have a common, there's no standard build system that we use for creating data sets that are even aware of the notion of dependencies. So I mean, to some degree, I think you can't build the NPM registry without thinking about the build system, and so I think doing those together is going to be essential for getting it right. And as an afterthought on that, a thing that's really important to consider here is not making sure that we trigger a lot of useless rebuilds of data sets, because especially if we're talking about large data sets, then something notifies another build system that some metadata in some underlying level 1 NASA data set has changed, and that causes all of the level 3 data sets to get rebuilt. Like, that's a huge waste of resources if it was a trivial metadata update. So I think we have to make sure that the build system can handle the protocol notifications as well.
Yeah, that's a great point. I'll just do a quick response to that. I think that one of the pitfalls with building catalogs in general is that people get too tempted to couple compute into the concept of a catalog too early on, and simply making something that sends out a notification which you are then free to act upon or to ignore is like a usefully scoped addition to what we have already. Whereas a lot of platforms that you see at the moment require you to like put your data in and also put your like workflow that's going to be triggered when the data gets updated. But one of the nice things about formats like Icechunk and Iceberg is because they're structured, your notification can contain essentially a diff of like what has changed, like have the chunks changed or have the metadata changed or has only some of the chunks changed. And then you can actually make like a more informed decision on whether or not you do need to like rerun your whole data set.
Okay, Simon. Oh, you're muted.
Hi, can you hear me?
Yeah.
Hi, so Simon Icechunk, I'm the tech lead of the Engine Data Catalog. So first of all, thank you, Tom. This is an excellent discussion. My general impression is this is impossible to build. We should try to build this anyway, because whatever we build is going to be useful. Just kind of my gut check. If you just try to do this for just remote sensing data, it'll probably require about 50 to maybe to 100 full-time engineers. So just to give everybody this idea of scope, which somebody has to pay for this infrastructure. So my general suggestion is, if you want to build something here, build something very, very tiny, like share 10 gigabytes over 2 organizations, share 1 terabyte over 5 organizations, just to try this out, because it will be tempting to jump immediately into protocols and all the cool technical stuff we would like to think about. But this is much more social than technical problem. So the social connections are the key here. We have lots of experience. I don't want to go into detail here. I'm happy to catch up, Tom, others, in private, just to give you an idea why this is hard. It feels, for example, the data set is a unique thing. The bigger it is, the more different they are. In theory, the engine has a copy of Sentinel-2. In practice, they are different in ways you can't easily describe in a schema. We don't have, the most recent assets of the last few hours. Worse, we don't have a few millions of assets because they have been reprocessed and we didn't catch up. We have all the versions of some assets, but not others because we didn't download latest versions. So there are for each interesting data set, there will be a lot of peculiarities, which it would be very, very hard to bake into a simple schema. So conceptually, this is much, much harder than just, a blue sky Twitter integration or whatever like this. But we should try anyway. So thank you.
Thanks, Simon. There's a lot there. I think just 2 points I can't respond to all of that. I'm not going to try right now, but I think just 2 points of clarification is one, I'm not suggesting anybody be moving terabytes of data with this network. I am simply talking about sharing URLs to where terabytes of data live. And then the metadata for what's in there, what's in that terabytes of data is stored at the URL. Or maybe it's duplicated in the catalog, but it's still only metadata. So we are talking about sharing tweet-sized objects across this FROTS network. We're not talking about sending actual data across this network, because that wouldn't be a proper separation of like storage from registries. Yeah. There are loads of other people with their hands up, so I want to pick on somebody else.
Yeah, let's move on to Adrian. You're muted.
Hello.
Yep.
Okay.
Yes.
Great talk. Thanks. I love being in a room with smart people, and I love Simon. I love the let's build it anyway. I love that energy. I'm wondering about the comparison to scienceonschema.org. Like, can you compare and contrast what you're proposing here with like a protocol that sends alerts to create a federated search interface? Can you compare and contrast that to scienceonschema.org, what they're trying to do, and how I work with polar data the most? I'm in Alaska, and I've worked with the Polder Federated Search Working Group. I see some of us in the participants list. Hello, everyone. Yeah, I'm interested in how this overlaps and doesn't with scienceonschema.org.
Thanks, Adrian. So basically every single time I show this idea to somebody, they tell me about some new platform that I've never heard of that's supposed to like solve this problem. I'm not aware of the scienceonschema.org, but I think what the blog post was an attempt to enumerate requirements of such a platform. And lots of the examples that I've seen fall down, especially on the requirements for scalability. And because I think that like the geospatial and Pangeo communities are basically the only ones that have really like pushed very hard on how you actually like encapsulate a petabyte of data as a single data set. And so to build this in a way that you can actually works for any data set of any size pretty much has to be done in this cloud native way. But as far as I can tell, most other fields have not done it that way. So a really notable example is like Zenodo, which has a maximum data set size of only 50 gigabytes, which for us is like nothing. Yeah, so I guess I don't know, but I'd encourage you to look at the explicit list of things that I wrote in the blog post, and then we could discuss more.
Okay, Sam.
Hi, thanks for the talk. That was really insightful. Two questions. One is the assumption here that most people already have all data sets in the world as cloud native formats? And the second question is there an incentive for commercial companies to do something like this? Because I've seen in the past where there have been some fears that a lot of commercial companies don't want to reveal where they task satellites, where they are actually collecting data. Because of commercial competitions in the same area, there might be some other interesting things that can come into it. And I've worked for two of the companies in the past, like I worked for Planet, I worked for Maxar in the past, and I run the community catalog. So I'm curious to understand, first of all, like, is the onus on the scientist, the student producing the data for it to be cloud native, or do you not care as long as it's hosted somewhere on the cloud with a URL? It's going to be an interesting one for people to make that jump, right?
Yeah, those are two great questions. This utopian vision is like premised on the idea that data is somehow accessible through HTTP range requests from somewhere public in the first place. That's often not true. Like it's often on some HPC machine or something that's not publicly accessible, but it's becoming increasingly more true for data sets to be on a bucket somewhere or behind some HTTP API somewhere. And that can be sort of virtualized within these sort of table and Icechunk formats. And part of the reason that I'm bringing this up now is that like this field of geoscience data sharing is in the midst of a transition of moving stuff to the commercial cloud. And so now is a good time to think about building a like complete catalog of where we're putting all that data. What was the second question?
The second
Oh,
question was
yeah,
about the commercial
yeah.
catalogs and areas of competition. But going back to the first question, Tom, I don't mean to like elongate this too long, but I will say that we are thinking very US and EU centric when we think about data practices, or the fact that people may not have the bandwidth or a commercial cloud availability to do the kind of transformations to their data, existing data even, and that is possible sometimes for people who are very well funded. So I will say that if you think about equitable, may not be equitable. I don't want to like, we can discuss this later. I just wanted to make that point, yeah.
Okay, I'll try and quickly respond to both questions. I see commercial cloud as a lot more equitable than what we've been doing previously in academia, which is to require someone to have a .edu email address before they can access like any of the services we built for them. Like you can log into an AWS data center in the US from anywhere in the world, and AWS will quite happily let you do that. And they will let you put data there. They will let you analyze data there. Somebody at some point has to like pay for the electricity cost of doing that. And there are various different funding models for that. Like maybe there should be a nonprofit that gives out like credits or whatever. But in terms of removing barriers to access, I actually think it's hard to think of a more equitable way than just like letting any anonymous user from using a service. On the tasking kind of like private data thing, that's a really interesting one. I think it comes down to like, if the data set is somehow paywalled, how much of the metadata gets paywalled? Like if all the metadata is paywalled, then they're able to like completely hide where the satellites have been tasked. If none of the metadata is paywalled, they're not able to hide that information. I don't have a good answer to that because I'm not familiar enough with that specific use case, but it's an interesting question.
Okay, Jed.
Yeah. I guess Tom gave my cloud talking points better than I could. I'm very leery of appearing to be a shill for AWS. I haven't worked there for years, but 100%. I mean, the thesis at Radiant is also that the trend is toward this distillation of data sets into URLs, and that commoditized object storage is what's making this possible, and that trend will continue. We're not there yet, and so obviously there's a ton of similarity between your vision and what we're trying to build with Source. I just want to clarify like a few things. Like part of our vision, I've done a bad job at like, I wrote something like a sketch of our roadmap down like a year and a half ago and haven't updated it since then. But like a lot of what you're describing is stuff that we do want to build into Source. And in fact, like I have this sort of jokey vision of a Source repo that would be, it would live at source.coop/source the organization. And then the repo would be called Source, and it would have like the source.catalog, which would be something very similar to what you're describing. You said, we can't have one organization run all of this sort of stuff. And I just wanted to make a comment about like the vision for cooperative SaaS that we have, which is that I'm very skeptical of federated solutions. I like the idea of them, but also to sort of echo Sam, there are a lot of places that like they're never going to be able to run their own infrastructure. And so there are benefits to having centralized infrastructure and centralized services. The trick is figuring out how to govern them and who owns them. And so that's the challenge that we're dealing with, which is how do we get the capital that we need to build a robust solution that like actually works really well and that people know about without selling our organization to investors. They're going to have different incentives. Now, I'm not against people raising investor money for different things, but we're trying to do something very specific, which is to solve that problem, which is how do we solve a centralized service that no one owns? And so a cooperative model is one way that we're thinking about that. Just to
be clear in what I'm suggesting here.
Yeah.
I'm not suggesting that. So my architecture diagram was supposed to illustrate the point that the platform services you can make centralized, and you can fund any platform service however you want, like cooperative, for-profit, like completely public sector, whatever. But there's still a benefit to having one of the underlying layers be a federated registry. And part of what I'm proposing here is that carving off just that part of like sharing the URLs is a part that it's like technically possible to federate that, and it benefits every platform on top of it if that layer is federated. But those platforms can be like a myriad of individually centralized services if they want.
Got it.
Yeah.
I see what you're saying. Okay.
Tyler.
I'm done.
I'm trying to understand, I'm a proponent of the cloud native formats and stuff, but I'm trying to understand why that is a requirement, that in the range requests, because couldn't a user just put like a CSV file on S3 and then make up a hash that corresponds to it, call it that version, and register it? So are those separable, basically?
I think
that
you
idea
could do
of
that.
being cloud native?
And I didn't really go down the rabbit hole of like what data formats are allowed, but I think that as long as your data format can go in an S3 bucket, be efficiently accessed by a range request, and uniquely specified by the URL on the hash, those are the only requirements you really need. And so your CSV example would fulfill those requirements. It wouldn't scale because you couldn't fit like a petabyte of data in a CSV without having some problems. But like you could imagine the registry pointing to the CSV data with hashes, pointing to Icechunk data, pointing to Iceberg data. But I chose Iceberg and Icechunk because they have some really quite unique and very powerful properties in that they are version controlled at rest in S3. So they're effectively like serverless formats in that you don't need to run any additional server on top of them to get like multi-tenant reading of multiple versions of the data at arbitrary scales. So like 80% of use cases can already be covered by, because arrays and tables are like two of the most popular types of data in science, then like 80% can be covered by those two, which is why I just listed those. But I see that as like an extension point, and your CSV example could be like something else that plugs into that extension point. Does that make sense?
I guess I'm still trying to think through like applications of this. Like maybe there is a lot of satellite data and crazy boundaries of the world, but those could be dependencies that are useful to just reduce down to like a very small table, like a CSV that has a count of something that's going on in the country or something like that, something that's really small. And it seems like a lot of users will be generating those data sets that are not going to be like in Iceberg or Icechunk, more so than users that would be aware and using those types of formats. So I'm just still curious of like, is that part separable? I mean, it's ideal if you actually can have a large data set and compare it to another and see what the difference is. That will be very valuable for in a notification. But I don't know if that needs to be a requirement.
Yeah, to be clear, I'm not saying that putting it in Iceberg or Icechunk specifically is a requirement. I'm imagining that putting it in some format which can be accessed via a HTTP GET request and uniquely specified by a URL and a version hash is a requirement. But like which format that is extensible and open.
Okay.
All right, Alex.
I can't hear you, Alex, even though you're unmuted.
Can you hear me now?
Yes.
Perfect. So I get the whole enchilada thing, and I have trouble envisioning, given the challenges of getting people to move data formats and platforms and all these things. I see this as like a 10, 20 years off. Maybe those early adopters would start implementing like something like this, and then it would grow. But if you want to cast a wide net and grab kind of the data that's already in existence, it seems to me like what you're really proposing is just some sort of standardization of metadata and metadata parsing. And you're requesting that there be specific fields in that.
So I have on this little GitHub repo I have for Frost, I have an FAQ question about this, which basically says, should we be standardizing metadata in any like domain specific way? And I see one of the strengths of Icechunk and Iceberg as formats is that they allow you to basically put arbitrary metadata in there, and they have space for arbitrary metadata, but they don't enforce anything about it. So you can put like CF climate forecast data conventions into ZAR metadata, but you can also put like neuroscience conventions into ZAR metadata. And both fields are quite happily able to get their metadata conventions into those formats and therefore into the catalog.
Okay.
I think that another way that various other like attempts to solve this problem fall flat is because they make assumptions about the metadata that are in some way like too specific. They're often like well motivated, but the result is they create a barrier for entry. And GitHub is a really interesting example here because GitHub requires nothing. Like you can put anything you want in a GitHub repo and it doesn't check anything about the metadata. It doesn't even require you to have a license. And so like I'm trying to keep this catalog schema at the absolute minimum. It's just like there was something at this URL. It's uniquely specified by this hash. It was created at this time, and that's basically it. And then the idea is that like communities who want to standardize on metadata can and should do that, but they can self-organize on top of that later. And all they need to do that is metadata to be available.
So it's a much simpler version. So you just want a registry for cloud native data that people could So what's the discoverability part? You know, like, so other than a URL, are people crawling the metadata themselves?
So let's just talk through what it would look like to build a discovery catalog on top of a system like this. Somebody like NASA or Source Cooperative or some platform service or something would run a replica of the database or something that consumes the updates. They pay a bit of money for that infrastructure, which is why it ends up being like slightly centralized or federated. They're ingesting all updates about all data sets, but each one is only the size of a tweet, so it's not that big. Then they are able to query that and filter it down in any way they like. So if they want to filter down for only the data sets that have like CF compliant metadata, for example, then they can. And then if they want to build a website that catalogs only the CF compliant data sets, then they can, and they can serve their user community like that way. And I think this is like part of the problem is that like everybody starts from trying to build something that serves a specific user community, but in doing so, because they tie it to the registry itself, their registry ends up unable to represent data that is outside of their community.
So
It's an interesting analogy in the blue sky world, which is this project I was linked to by Alex Moreau called Black Sky, which is basically like a safe space for the Black community online after Twitter was overrun. And the way it works is that the person who runs Black Sky consumes the fire hose of every update that comes from the entire Blue Sky social network. And then he automatically uses services to filter out like hate speech before showing it to a specific community. And it's funny because that's kind of analogous to what I'm suggesting. You accept that instead of filtering out hate speech, you're just filtering down for only like oceanography relevant data sets or something like that.
So are you looking to define what the minimum schema is in order for something like this to be useful?
Yeah, and I'm saying that the minimum schema should be like absolutely nothing specific to like CF conventions or satellite data or bioscience or anything. It should just be like, there is a data set at this location. It's uniquely specified with this hash and it was last updated at this time. And then you should just like stop there basically, because that's already very useful, especially with the update propagation. But that's a good primitive for people to then build upon.
So does that, if you don't have anything, doesn't that make it eventually kind of impossible to parse? Doesn't it just keep growing and growing, and I can't build an earth science data set or database because I don't know what metadata to go look at. So I would be
What
opening
metadata
up
to go look at is a field specific problem. Like only earth scientists will know what metadata to look at. And they won't even like what metadata to look at will change in 5 years when they change their standards.
But if you have a trillion objects to data, and you want to know something about that data, and it's not in your schema, how do I discover something about that data?
Yeah, so this is the question of like the metadata lives like one of the major unsolved questions here, which you're getting at, is like the metadata can live in the bucket, and in Icechunk or Iceberg, the metadata lives in the bucket alongside the data, which is good because the data is self-describing. But you could also take that like ZAR JSON and copy paste it into the catalog entry as well if you wanted to. That would be like an arbitrary metadata field that contains like any string dict thing. And so you've not made it domain specific by doing that. And that would allow you to then query on the layer of like the individual tweets, right? But the important thing is to resist the temptation to not go any further than that. You're right that like you want that there for discoverability, because otherwise every single time a data set is updated, you have to go and hit the bucket to go and get the metadata. The only hesitation I have about doing that is like then you have this like consistency problem of trying to ensure that the metadata in the registry entry is the same as the metadata in the bucket, but that's not unsolvable with like self-hashing data structures and stuff like that.
Is it okay if we move on to another question? We got a couple more people. Ryan.
Okay, you hear me? Yeah. Fascinating stuff. This is great. Thanks, Tom, for like stimulating such a thought-provoking discussion. I want to take it in a little bit different direction and talk about what I'm excited about with this proposal, which is not what we've been talking about so far. We've talked a lot about metadata and catalogs, and I think we can argue about whether it's a Sisyphean task to like organize all of the scientific data in the world through one framework, or whether the world is just too inherently chaotic for such an effort. But I'm interested in a much sort of like tighter scope around this sort of mechanics that Tom described. Don't care about metadata really. Like, what is novel and innovative about what we've done in this community is to move beyond this idea that like data is represented as files, which is like the sort of baseline status quo for like, of course, data is files. Like, what else is data? And I think we've been very effective at pushing forward this idea. It's like, well, no, like the files are just like an implementation detail, and the data set is this sort of logical object. And we've defined some sort of structure. So like ZAR and Xarray have been very useful for doing that, because it sort of transcends a file, but it maintains sort of a data structure. And then obviously, mainstream database style structured data, tables are another example of that. And over in tabular data world, there's been this interesting convergence where they are most tabular data systems are now also based on just some files in object storage, Parquet files specifically. That's where things stood a couple years ago. And what has been even newer to that is to really bring these sort of database style transactions on top of that data, so that we can define an update to a data set beyond just like, oh, I uploaded another file, into something much semantically richer, like I inserted n rows into this table, or I wrote to this region of the array and created this metadata. And so that's why, Tom emphasized specifically Iceberg, Icechunk. We could point to, Delta Lake, or any number of similar transactional formats. They're very, very important for science and scientific reproducibility, because they have immutable, state, right? Like, this is the problem with just a URL. You send me an S3 URL or any URL, it's not immutable. There's nothing about it that like tells me whether or not it has changed. And so by itself, it's just like not as useful in this sort of context of a data system. You have to like have some out of band mechanism to know if whatever is that URL is the same thing that it was yesterday or a year ago. But now with these new cloud data formats, we're going to a much more database style interaction with the data. So what I'm excited about with Tom's proposal is this idea that we can chain relationships together and build reactive and responsive data pipelines that update based on one data set that's updated, and like another data set then gets updated in response, and potentially doing that in a very efficient and incremental way, leveraging the metadata that's present in those formats. This is something that Gavin Schmidt, the director of NASA GIST, like always asks me about. He's like, why don't we have all of these derived data sets from CMIP that are just like automatically computed? Like, why does everyone have to recompute like the climatology of each model, or like the global average surface temperature? It's not part of like the primary data set that's distributed, but it's like very deterministically produced from the original data. So I'm interested in exploring Tom's idea on a much smaller scale. Forget about the global and aggregation of all the data. Can we literally just take two data sets and chain them together, so that when I update data set A, data set B automatically updates, and use that as a sort of proof of concept for what this type of architecture could enable. And I just posted like a few papers and concepts in the chat. I've been spending time reading about streaming data systems and database theory, incremental computations. I think this is an extremely rich area of technology that our community should explore. There's a lot of potential here.
Could I just jump in here and say, we have 2 minutes left before the top of the hour. We can keep on going. But before people start dropping off, I did not hit the stop record button. And I just want to make sure if anybody is upset with that, I chose not to do that after Tom said this would be a very valuable part of the discussion. But if people are concerned about that, let me know and I can edit the video. And, but I didn't sense that anyone, was worried by that, but please let me know if you are, and I can chop the video. But I am going to stop. Actually, Jed, do you want to ask your question? You had your hand up.
No, actually, Ryan started hinting at this a little bit in the chat. I think there's looking at the stat catalog specification is kind of like the core, like how to just like sort of tweet sized, how do you describe a data set is something that I'm interested in working on too.
I see Stack as a domain specific, like really good example to follow of domain specific metadata that should go in a general catalog. Like the Stack people have clearly got it worked out for their specific use case of like data sets that refer to some view upon the planet Earth.
Well, what I'm arguing for though is
science have an equivalent.
Yeah, what I'm saying though is that like the high level Stack catalog spec is very generic. Like it could be used as inspiration for this. And we're thinking about doing that with, for example, Source has its own model, which is like you have a title of a data set, you have a description, you have who created it, and you have some objects. Like that's it, and a URL. Like that's it. So anyway, interested in hacking on this with you because I think we need this sort of like core set of metadata for data products. So
and just to clarify, in case you missed it, Tom, you are you'd like to continue this conversation with a group of people who are interested in the subject, right?
Yes, I'll post the URL link again.
All right. Yeah, thanks everybody. Thanks, Tom. We didn't get to the check-ins, but that's okay. You can check the doc and or you can check in next time. So thanks again, everybody. This was a great conversation. We had 50 plus people on the line, so it's awesome.
Thank you.
See you next week.
Thanks, Tom.